Hi, this is Han in MCDB 427 Molecular Biology at University of Michigan. We are going to learn about an assay to map nucleosome-free regions by using DNase I cleavage and sudden blot. It corresponds to the figure 13.16 and 13.18 in Molecular Biology by Robert Weaver. This is a cartoon of the SV40 genome when it is complexed into chromatin. SV40 has a circular genome of 50 to 24 base pairs, and transcription of all mRNAs occurs divergently from a promoter region called the control region. The blue balls represent nucleosomes, which are DNA complexed with proteins called histones. Also shown are three restriction enzyme cleavage sites indicated by green arrows, which will become important in a bit. Prior to the experiment, I have to tell you that Yaniv and his colleagues already knew that nucleosome-free regions exist and where they were. For smaller size of DNA such as plasmid, it was possible to distinguish whether the part of the DNA was complexed in nucleosome or not with microscopy. However, it was hard to have more precise location of the nucleosome-free region, and it cannot be used on large molecules like the chromosome. In order to overcome the limits, they wanted to develop a new assay that was more generally applicable. They came up with the brilliant idea to map nucleosome-free region with DNase I cleavage and sudden blot. Nucleosome-free regions are more accessible for enzymes cutting the DNA, and one of them is DNase I. DNase cuts DNA randomly, and when we keep it at limiting concentration, it specifically cuts nucleosome-free regions, preferentially over places where there is nucleosome. We can call the nucleosome-free regions hypersensitive site for DNase. Let's go over how we can locate hypersensitive site with DNase cleavage and sudden blot. They first allowed SV40 to be in the monkey cells in 24, 34, or 44 hours, and the chromatin from the cells with SV40 were isolated. Thus, there were three different time periods from infecting the cells to harvesting the chromatin. Then we cut the DNA with DNase I in low concentration. Theoretically, DNase is only going to cut at the control region, especially when DNase is in low concentration. After that, histone proteins in nucleosome were removed. If we just took the molecule and run it on a gel, we will just get one linear plasmid and we won't get any information about where DNase I cuts. So we cut it with restriction enzyme that has the known site. In this experiment, EcoR1 was used to cut the DNA. Then it was run on a gel. Even though it looks like we are going to get distinct bands on the gel from the cartoons, in the real experiment we won't. We will just get a smear of bands because we isolated nuclei from monkey cells infected with SV40. So there are going to be tons of bands in all different sizes. So we are going to perform sudden blot in order to figure out what exactly we are looking at. First, we blot the DNA fragments on the filter. Then we denature the DNA on the filter. After we do that, DNA fragments on the filter are now single-stranded like the cartoon here. And finally, we incubate it with the probe. In this experiment, they radiolabeled the whole SV40 DNA as the probe. The data on the right is the result of the sudden blot, and let's go over that. We need to be careful with the labeling because the numbers on the right are not the measurement of the size in kilobase. It is the relative percentage of the size of fragments. So 100 means it is the 100% of the genome, so it is the full length of it. And for instance, 67 means it is 67% of the genome. I also put the size in kilobase to the left of the data for you guys to have better understanding. Let's go over the data. On the top of the data, the band at 100% is running as 5.2 kb. We know that SV40 genome is 50 to 24 base pairs, so it is the linear SV40 DNA. Since the EcoR1 digest was to completion, all of these DNAs were cut just once by EcoR1. If the DNA was also cut by DNase, this full length of DNA should be cut. Then what can we learn from the bands running at 67%? It means that DNase cuts the DNA 67% of the genome from the restriction site. And if we do the math, the rest is 33% of the genome from the restriction site. And this is how the fragments will look like. Here is another cleavage site that is 30% of genome away from the restriction site. And the rest will be around 70% of the genome away from the restriction site. And the cartoon indicates the two bands from the data. Now you may be wondering why we see a cluster of bands from 26 to 33 but just a single band at 67%. 26 and 30 tell us that it is selectively cleaving at 26 and 30% of the genome within the control region. In addition to that, the reason why we do not see 74 or 70 is because 67 to 74% is a range of 3.5 and 3.8 kb, which is harder to perfectly resolve than 1.5 or 1.3 kb from 1.7 kb. Because they did not resolve any of the larger bands on this gel, they just labeled them all 67%. Similar to the last two, there would be a cleavage by DNase at 26% of the genome away from the restriction site, and the rest is around 74%. And this cartoon corresponds to the bands in the red boxes on the left. Now you may wonder that control region could be on the other side of the SV40 based on this experiment, because all we know is the relative size percentage of plasmid. This assay may be less clear to work with plasmid, especially when there are only two digestions. But if you watch another video about an experiment of mapping hypersensitive site near hemoglobin gene control region, you are going to have a better understanding of the assay. We learned that DNase cleavage and sudden blot can map nucleosome-free regions. The experiment supports the hypothesis that hypersensitive sites are at nucleosome-free regions. Thanks for watching and go blue!